please, gentlemen. Thank you for quieting down. Thank you, thank you. All right, a couple quick reminders. Friday's lab, 5 pennies, shiny pennies, please. 3. Three is what you need, 5 is better. Shiny pennies so that you can do the lab. Also, in order to do the lab, we need to have your lab safety sheet. If you haven't already turned that in, you have to have it in by Friday. If you don't have the lab sheet in, you don't have access to the lab. You don't have access to the lab, you can't do the lab. You can't do the lab, you can't get a grade on the lab. So please get that in. There's 7 of you as of yesterday, so these numbers might have changed a little bit, but 7 of you that have not turned in your Rutherford lab from a couple of weeks ago. That window closes even for late work on Wednesday, 1 week from today. So if you don't have it done by then you're not getting it done at all. Same story for the mole activity. I'm not sure how many of you are missing that, but if it's you, if you haven't done it or you haven't turned it in, it needs to get done by Wednesday, and you need to get it turned in so you get some points for it. Element quiz, that's Friday. That was from a month ago. Some of you took it, didn't pass it, never retook it. Some of you took it, didn't pass it, retook it, still didn't pass it, and still haven't passed it. And a couple of you people haven't taken it at all. That's no es bueno. But you need to take it by Friday. You need to get a pass by Friday. If it's no pass, no score. So zeros are going in there. That's a big freaking 0. 0 out of 46 is big. So, and don't tell me you're not ready, you haven't had time, because it's been a month. So let's take care of that business right away. Today we've got chemistry calculations. You should have one of these handouts. Note-taking sheet. You're going to get a worksheet before you leave. We'll go through it as quickly as I can. The more you pay attention and ask questions, the quicker things will go. If you have questions, if you don't ask questions, I'm just going to keep rolling. But we've got quite a bit of material to cover, so let's get busy. So first, taking measurements. This whole discussion is going to be about measurements and meaningful numbers in measurements, and what do we do with those meaningful numbers in measurements, and what is a meaningful number in a measurement. But first, what is a measurement, or what do we need to do when we take measurements? The first thing we need to do when measuring, using a measuring device, is to look at that measuring device from directly in front and at eye level, so that you can get a good, accurate reading of what that measurement is. We do that from directly in front and at eye level so that we can avoid what are called parallax errors. Parallax errors are when, well, parallax is when something appears to be in different locations when it's viewed from different angles. So just as a quick example of that, if you close one eye and put your thumb in front of something, a periodic table or something, you'd be able to see that the thumb is in front of whatever you're looking at. If you switch eyes, all of a sudden your thumb's not there anymore, or it's not behind your thumb anymore. So that object hasn't moved. It just appears to have moved because you're looking at it from a slightly different angle, which is what gives us our three-dimensional vision, because we've got binocular vision, because we have 2 eyes. Each eye looks at something from a slightly different angle. So when I look at Daniel with this eye, I see this side of him. When I look this, I see this side of him. I take those 2 images. They form an image on my retina, sent to my brain, and I see in 3 dimensions, so I'm able to have some depth perception. If you only have one line of sight, no depth perception. If you don't have it, you wish you did. Okay? Secondly, when we're looking at an object or a quantity that we're trying to measure, we want to write down as many digits as we can for certain. So if we take our little eye and we move it down here, and we're looking at that liquid measurement from directly in front and at eye level, we can clearly see that that is at least 40 but less than 50. So the volume is going to be 40 something, but we can be a little better than that. We can estimate one digit beyond. One and only one. So, whoops, we're a little off calibration here. There we go. So that's somewhere between 40 and 50. You might estimate it's 47. Somebody else might estimate 48 or 49 or 46. Those are all equally good. There's not a right answer because it's an estimate. And in math, numbers are exact. 12 in math is the same as 12.0 or 12.0000. In science, when we're taking measurements, there's a big difference between 12 and 12.0 and 12.000. So by convention, everybody in the scientific community knows that the last digit in any measurement is an estimated digit. So those are our three basic rules for taking measurements. So I've given you one example already. Here with the beaker, that's calibrated to the nearest 10 milliliters. So we should always be able to record our measurement 1 degree of precision beyond the calibration. So since we know the nearest 10, we should be able to estimate it to the nearest 1. Or if we take that one step further, in this example, speaking of calibration, I don't know what happened to our screen over the course of the last period, but in this example, our graduated cylinder is marked in tens of milliliters, 20, 30, 40, 50, 60, but it's also marked in single milliliters, so tenths of a 10. So we got 51, 52, 53, 54, all the way up to 60. So we should be able to look at that from directly in front and at eye level and say that, for example, that is at least 56, and we're going to estimate how far it is between 56 and 57, and maybe it's 56.4 or 56.5. But this last digit, everybody will know when they read your data, is your estimated digit. So they will know with a high degree of certainty that it's at least 56 and less than 57, and that last digit is just your best guess. That's fine? Okay, so those are the meaningful numbers in a measurement. That's what we mean when we refer to significant figures. You're going to hear that term a lot in the near future. Significant figures are the meaningful numbers in a measurement. So in that first example, when we're writing down that it's 40 something, we're going to say 47 or 48. That 7 or 8 is definitely a meaningful number. That's a good guess. But because we don't know for sure if it's 47 or 48, we sure as heck can't say that it's 47.2 or 47 and a half, because we're already guessing about the fact that it's 47 or 48. We can't guess beyond our guess. So 47 point something would not be a meaningful number. 47 or 48 is a meaningful number. When you look at someone else's measurement, someone else's data, you should be able to determine how many of the digits, numbers in that data are meaningful. And so there are rules that we follow, that the entire science community follows, to determine which numbers are meaningful numbers in a measurement. If they are non-zeros, they're always meaningful. They're always considered significant, because the fact that it is a non-zero indicates that it was measured and, in the case of the last digit, estimated. So this guy has 4 significant figures. Every time we have a non-zero, that is known to be a measured or estimated digit. The only thing that gets dicey is zeros. Zeros that are between non-zeros, or zero sandwiches, are always significant. Just because it's a zero doesn't mean that it's an estimated value. Some values are measured to be zero. So this value, 5005, would indicate that we think that answer, that value is somewhere between 5,000 and 5,010. So we know it's at least 5,000 and less than 6,000. It's definitely less than 5,100. It's definitely less than 5,010. And this last digit we're guessing is about halfway between 5,000 and 5,010. So this also is going to have 4 significant figures. Then finally, in terms of zeros that are significant, if they are trailing zeros after the decimal. So they're after some non-zero. Non-zeros are always significant. But it's after this 2, and it's after the decimal point. So the fact that we write those 2 zeros indicates that not only do we know that it's at least 1.2 milliliters and less than 1.3, we're not even estimating, we know that it's 1.20, and then we're going to estimate that last digit, which we're guessing is a 0. So we not only know it to the nearest tenth, we know for sure that it's 1.20 to the nearest hundredth, and if it happens to be right on that line, we can call it a 0. Somebody else might say it's 1.201, but our estimate was 0. So that, again, is 4 significant figures. Not every number has 4 significant figures, even though each of our 3 examples have 4 significant figures. So far, so good? The last zeros that we deal with are placeholders. Those are not significant. The purpose of a placeholder is to tell us how big or how small the non-zeros are. So if we got 5,000, these zeros are not significant. All they do is tell us how big that 5 is. Because clearly there's a big difference between 500, 50, or 5,000, or 50,000. So how many zeros we have behind it tells us how big that 5 is. This has 1 significant figure. That means that our best guess is it's somewhere between 0 and 10,000. We think it's 5. You might think it's 6. It's a big group of people at a concert, and you're looking out and you're seeing thousands of people. You know it's not 20 or 30,000. Think it's less than 10, and your best guess is it's about 5. And going the other way, if we have 0.0005, all those zeros are placeholders. Their only purpose is to tell us how little that 5 is. So that again is just 1 meaningful digit, 1 significant figure in that measurement. So there's 4 rules. Might seem like a lot. Some of us like rules, like to be very analytical. If you don't like rules and you just want a simple device for remembering how to figure out how many significant figures there are, we've got the Atlantic and Pacific rule. We all know that the Pacific is over here and the Atlantic is over here. P for Pacific is the same as P for present. We're looking to see if the decimal is present in a number. So for example, 0.00025, there's a decimal there. The decimal is present. So we're going to start from the Pacific side, the left side, and we're going to come across until we reach our first non-zero. And once we do, we're going to count all the digits after that. In this case, there's only 2, but if there were more zeros or numbers behind that, we would count those as well. This has 2 significant figures. If the decimal is absent, we're going to start from the other coast, from the right coast. And we're going to keep going through all those zeros until we reach our first non-zero, and then we count everything after that. So that also has 2 significant figures. 2,500 with a decimal behind it. That's one way to indicate that we've measured that to the 0 position. So we're going to come from the Pacific side, 1, 2, 3, 4. All 4 of those digits are significant. That's a lot more precise than 2,500, which if it was just 2,500 without the decimal, that would say that we think it's between 2,600 and 2,700. This tells us that we think it's between 2,500 and maybe 2,499, maybe 2,501, but we're guessing that last digit is 0. And then finally, this decimal is present again, so we come from the Pacific side, get that first non-zero, 1, 2, 3, 4, 5. As we said, the trailing zeros behind the decimal are still significant, so that number we know to a high degree of precision, all the way out to the 10 millionth place. And that's got 5 significant figures, 5 meaningful numbers in that measure. Giddy up? Questions so far? Okay, some of these numbers are really big and really small. We want to be able to write them in a shorthand method, scientific notation. I'm guessing that the majority of you are already familiar with scientific notation. If you're not, we're going to show you how to use it. If you are, here's a quick review. We use it for a number of reasons. 1, to write really big or really small numbers. 2, to identify the number of sig figs. And 3, to get a good estimate of how big or small that number is. So we'd just be able to look at that number in scientific notation. It'll tell you right away. Are we talking about millions? Are we talking about thousands? Are we talking about puny little fractions? First rule for scientific notation is the general form. M is your base number times 10 to the x power. This base number m is going to be greater than, could be equal to 1, always going to be less than 10, which means there's only going to be one non-zero digit in front of the decimal. So there's a couple of examples there. It could be 1.0, it could be 1.1, it could be 3, it could be 3.3002, but it'll never be 11. It'll never be 22 in front of the decimal. Just one digit in front of the decimal. When we write these, we're only going to write the significant figures. I skipped that second one for a reason, because I wish in hindsight I'd have flipped the order of them. So when we write a number in scientific notation, the only digits that go in our base expression are the significant figures, which is nice for you, because if you see a number in scientific notation, all you have to do is count those digits and you know how many significant figures there are. And we'll go through a couple of examples in just a moment. And then finally, in order to get one non-zero in front of the decimal, we typically have to move that decimal point. How many places we move it determines what the exponent is going to be. Every time we move the decimal to the left, our exponent gets larger. Left. Larger. When we move the decimal to the right, the exponent is reduced. If we're moving the decimal to the right, it's because it's a puny little number. It's less than 1. So we got to move it to the right to get something in front of the decimal, which means our exponent is going to be some negative exponent. So let's look at a couple of examples here. We've got 4 of them. First one, 6,809,000. How many significant figures are in 6,809,000? 4. Good. We know our non-zeros are significant, and our zeros between non-zeros are significant. These other 3 zeros, they're just placeholders, not significant. So we got 4 sig figs. Now we got to move our decimal place. How many times? I don't see a decimal. If it was there, it's an understood decimal point way at the end of the number. We're going to move it 3 times and 3 more times. So a total of 6 times, so that we only have 1 digit in front. Which means our expression is going to be 6.809, because we're only writing the significant figures, times 10. We move the decimal left 6 times, so our exponent gets larger by 6. Starts at 0, goes up to 6. These things practically solve themselves. 0.003400. How many sig figs? 4 again. Non-zeros, 3 and 4. Trailing zeros after the decimal, or the decimal is present, so we come across from the Pacific side and count everything after that. So we got 4 sig figs. Now we got to move our decimal point how many places? We've got to get that 3 in front. 1, 2, 3. So 3 times to the right, our exponent is going to be reduced by 3. That gives us 3.400. We're writing those zeros because we already determined that they were significant. Times 10 to the negative 3, because we moved it to the right. Why do we move it to the right? Because it's already a puny little number. Our negative exponents are for puny numbers. What if we want to go this way? Well, it's not so bad. We know how to go from standard notation to scientific notation, so we just go in reverse. We got 8.35 times 10 to the negative 6. The fact that it's negative 6 should tell us right away, puny number, puny number. It's going to be little. We had to move our decimal 6 places to the right to get it into this format. So we're going to move it 6 places to the left to get it out. 1, 2, 3, 4, 5, 6. So this is where our decimal used to be. All of these are zeros. And so to transform that into standard notation, we're going to have 5 zeros and the 8, so 6 digits, which corresponds to our negative 6 exponent, and we still have that 3 and the 5. One more time, just for kicks and giggles. 10 to the third. That's a big number. So we should expect a big number as our result. We move it to the left to get a larger exponent, so we're going to move it to the right to get back out of our scientific notation, 1,202, or 1,202. Giddy up? Any questions? Try to keep things moving. I know it's a little toasty in here. All right, so we got these measurements. We know how to write them in scientific notation. We know those measurements represent meaningful numbers. Let's talk about significant figures in math. This seems like a good time for a transition. Thank you, Mr. Kelleher. You're welcome.
All right, we're switching. All right, so sig figs in math. So sometimes you have to do a calculation with a significant figure measurement. So you may have made a measurement and it's got some significant figures to it, and you're going to punch it into your calculator, but your calculator doesn't know it was a measured number. Your calculator does math. Doesn't necessarily do chemistry math or science math. Some of them actually do, but very few people I know how to actually use their calculators to be able to do that. You have to actually tell your calculator that it's a measured number. So when we're going to be doing these, we have to be kind of paying attention to the significant figures, because when we represent that measurement, when we calculate with it, we can't write and say that we suddenly end up with a more accurate or a more precise measurement than what we started with. That's impossible. You can't have that happen. So there's a way that we do that, and we have these rules for doing that. So there's really just two different rules, depending on what math you're going to do. The first type is if you have multiplying or dividing. The rule for multiplying and dividing, you should write that down, is that your final answer has the same number of sig figs as the least precise number in the calculation. Sometimes it's convenient that they both have the same number of sig figs. Well, that's easy. Your answer should have that same number too. Our first example that we have up here, we've got 4.56 times 1.4. We're assuming that those are measured numbers. These have certain number of sig figs here. So when you punch that into your calculator is just going to do math and just spit out a number. But a lot of times you're going to have those extra decimal places. Remember, people were always asking us, like, how should we round this? Well, now you're learning how. We're going to learn how you're supposed to round these. Because yeah, you can't say that if you have a measurement that only measures to the 10th place, or a measurement that only measures to the 100th place, and now you've got like decimals that go up to the like billionth place. There's no way you should be able to write that down because there's no way you could measure that. That's impossible. So we take a look at our first example here. 4.56. How many sig figs is that? 3. That's 3 sig figs. So that's 3 sig figs. 1.4, how many sig figs is that? 2. 2 sig figs. So when we punch it into a calculator, the calculator comes out with an answer of 6.38. According to our rule, we should only have how many sig figs in our answer?
5.
Not 5.
2. 3. 7.
2. Should be 2. Final answer has to have as many sig figs as the least precise number. The number with the fewest sig figs. We said it's got 2. So our answer should have 2. So we need to round this. To 2 sig figs. And we're just going to follow the rules of rounding that math does. Science technically has one weird rule for rounding that we're not going to talk about because it's confusing. It deals with statistics of measurements. Don't worry about that. So I'm going to start with going, doing my Pacific route, going from left to right because my decimal point is present. I hit the 6, that's 1 sig fig. And then I hit the 3, that's another sig fig. So that's my 2. I've hit 2 sig figs. So right here is the spot where I need to report my answer to have 2 sig figs. But the digits that come after that are also kind of important in terms of knowing what kind of number I should represent as that last estimated digit. So since it's an 8, what should I do to my number 3 there?
Change it to a 4.
Round that up. So my answer should be 6.4. That should be your answer that you would round to doing that calculation if those two numbers were measured numbers. Our next example, we got 50.0 times 96.5. How many sig figs is 50.0?
3.
That's 3. The decimal point is present, so those zeros count. So this is 3 sig figs. 96.5. That's 3, because there's no zeros there. Gotta love measured numbers that have no zeros in them. Makes it easier. So my answer should have how many sig figs? 3. So I need to have 3 sig figs in my answer. Because both of these were 3. That was easy. They're both the same number. My least number is 3. So I need to round this to 3 sig figs. So again, I start from the Pacific side. Keep going. I got a 4. That's 1. 8 is a second. And then my 2 would be my 3rd sig fig. So that's where I should end my measurement. The 5 tells me I should do what? Round that up. So that will become 4,830. Because that last 0, without putting a decimal point, is not significant. So my 4,830 is only 3 sig figs. So those zeros are a little tricky. Sometimes they can help us out a little bit. Sometimes they can make it confusing. Question?
Can you show how the 50.0 has 3?
Okay, how it has 3?
Yeah.
Here's how I kind of remember it. My rule is, why would you have written that if you didn't have to? It's kind of a thing. If 50 is the same thing as 50, and that's the same thing as 50, what's the point? The reason is because it depends on what level of measurement did we make. This only has one sig phase, because we're saying that we don't know for sure what this measurement is. It's somewhere between 40 and 60. We think it's about 50. But that gives us a big range. It could be anywhere from like 45 all the way up to 55. It's somewhere around in that range. By putting a decimal point here, that tells me that, oh, I know this one. This is between 51 and 49. So I'm getting a little bit closer, a little bit more narrowed in. By putting another decimal place, oh, this is between like 49.9 and 50.1. So I'm getting even more. So the more stuff you put there, the more information you're getting about that measurement. That's an excellent question. Because I always got annoyed when I was in high school. I'd write an answer in math class of like 0.5. And my math teacher would be like, wrong. But the answer's a half. Then you write 1/2, like 1/2, because that is an exact value. That means 0.5, infinite number of zeros going after it. So I'm like, okay, all right, whatever. And I go to science class and I make a measurement, and it'd be like a 1/2 inch, and I write down 1/2. And my science teacher would be like, that's wrong. That's too exact. You can't say that. You can't say you measured it out to 0.00000 forever, because you'd still be measuring it. I was like, oh, okay. So math and science they always sometimes deal with numbers differently. And that's the tricky part you got to kind of get used to. It's a little bit of annoyance. Our other rule that we have is adding and subtracting. Adding and subtracting is a different rule. It is, you have to look at what's the least precise measurement that you have. Not total number of sig figs. It's just kind of where does the sig figs end at. So your final answer has to have that same level of, the lowest level of precision that your measurements have. Not just number of sig figs. It's a little different. Don't mix them up, because that'll get you the wrong answer. Your final answer, same number of decimal places as your least precise measurement. So which one of the measurements ends first and doesn't keep going? 18.0 in this example. Because 18.0 only measures to the tenths place. The first number measures to the hundredths. That's a little more precise. It's getting a little bit further down the road there. And our bottom number measures to the thousandths place. So when I'm doing the math on this, your calculator comes up with this answer. But we don't know for sure what these digits are here. So we can't say that we know that 2 and that 3 for sure, that that's exactly those numbers. We can't say that. But we can say we do know to the tenths place, because we do have tenths place from our other measurements. So we round to the least precise measurement, which was our 18.0, which is the tenths place. So our answer should be rounded to the tenths place. So since after the 0.1 in our answer, we have a 2 and a 3, we round that down. Let's get rid of those. Before we round it up on these two, this one we didn't have to round up. So it's the same rounding rules. But you have to obey the rules of your sig figs, though, in all your calculations. Any questions on that? Cool. You're going to get some practice in this coming up. All right, the next thing that we have is a bunch of stuff that we're going to just kind of skip through. All right, let's do a couple of examples of calculations that you might actually have to do in a science lab. Still, people, quiet down, please. So here's an example. I think it might be on your sheet. Yep, looks like it's on there. Okay, so one of the topics we're probably going to get into pretty quickly is dealing with like measuring density, which you have to measure mass and volume. So if you have a balance in a graduated cylinder, the balance for measuring mass, the graduated cylinder for measuring the volume, we get this data that's here. We get a mass of 18.9 grams. The volume of water in the graduated cylinder when we started was 30 milliliters. Then we dropped whatever that sample was into the graduated cylinder, and the water level goes up to 35 milliliters. So we want to calculate the density But we have to obey rules of sig figs because these are measured values. First thing we have to do is we have to figure out what was the volume of the sample. So we subtract. We're going to do a subtraction there. 35 milliliters minus 30 milliliters gives us our 5 milliliters. That's the volume of the sample. That's the sample volume. Whatever that was, like a tiny little rock, or maybe like a marble or ball bearing or something. Then we need to do the density equation. Density is mass divided by volume. We've got the mass was 18.9 grams. And now we've got the volume is 5.0 milliliters. We had to keep that 0 to have the right significant digit spots. 10th place. So our last thing then is to do that division. Take that mass of 18.9 and divide it by 5.0. But this is a different calculation. This isn't adding, subtracting, this is dividing. We have to follow the other rule. So 18.9 has how many sig figs? 3. Yeah, there's no zeros in there, so 1, 2, 3. 5.0 is how many sig figs? 2. That last 0 does count because the decimal point is present. So our answer can only have 2 sig figs. So it's 3.8. It's rounded to that. Because if you did this in your calculator, you're going to get a bunch of digits. You have to round it to 2 significant digits. 3 point, and that next digit is going to be your significant one. Any questions on that one? Good.
Yeah, this is kind of confusing. Yeah, this is really
Is this confusing? Well, we got a worksheet that kind of hopefully will help you out. All right, on your note sheet, you have another spot that says it has like an area of like a circle. You can skip that out. You can cross that part out. Don't worry about that. We're gonna go to the next one, the volume one. This is one you guys can do pretty easily, I would Okay, so volume calculation, length times width times height. And we've got a solid block. We have its dimensions, 2.7 centimeters by 1.6 centimeters by 6.3 centimeters. That's a pretty tall block. All of our measurements have just 2 significant digits. 2.7 has 2, 1.6 has 2, 6.3 has 2. So when you calculate this out, your calculator comes up with an answer of 27.216. But this is a multiplication, so what rule do we follow for our sig figs in our answer? Be the fewest number that we had in our problem. So it's all the same, 2, 2, and 2. So our answer should have how many sig figs? 2.
I guess.
So I start from the Pacific side, I come across, I've got 2 as a significant digit. 7 would be a significant digit, and that's 2. After it, I've got 0.2, so should I round that up to 28? No. My answer is 27. And my unit would be centimeters cubed.
I thought it was supposed to have the same amount.
It does.
So you basically just cut off the decimal.
Yeah, you just drop those off. There's a reason why you do it. Trust me.
We're going to find out that.
No, because that usually just confuses people.
I'm already confused.
Well, then there'd be even more
My
confusion.
brain
Any other questions about that one? Like I said, the more practice you get with these, the better off you're going to be. All right, just got a couple more slides to go and then we're done.
I like the arrow.
Percent error. With percent error, a lot of these calculations we're going to do later on are going to relate to like measurements they're going to make in lab. So it says actual value versus experimental value. So a lot of times this is going to be like a measured value versus an accepted. So sometimes you'll see it written this way: accepted value and your measured value. And then you divide that by the accepted value.
Experimental measure.
What are we doing?
It's the measured value, so it's what you
You can write down
actually
both of
find.
them. Write down both of them. Actual minus experimental divided by the accepted. And then above actual, write accepted. And above experimental, write measured. And the little bars on the outside mean absolute value. We don't really care if it's positive or negative. We want to know how close we are. If it was negative, it means we came short of the accepted value. Positive means we're over the accepted value. We don't care about whether we're short or over, just how far away from it we are. So the absolute value bars are in place.
Let's take it back 5 steps. Back to
Nope, can't do that.
Okay, why don't we So are we just skipping those 2 other problems?
Yes.
Then cross them all?
You just cross those out.
Area,
Take them in.
Alright, people, we can bring this back real quick. A lot of the chitter chatter going on. You need to kind of keep that to a minimum so we can try to reduce. I understand some people are frustrated with where we're at right now, but we have to keep moving. We got one more thing to talk about after this. Unfortunately, we're not going to run into percent error for a little while in our lab experiments, but you will get very familiar with this calculation, believe me. So here's an example. You got the mass of a cylinder to be 19.8 grams. The actual factory reported mass of that is 20.0 grams. What's the percent error of your measurement? So the actual value or the accepted value is whatever it's manufactured to be. In lab, it'll be like, this is an actual amount that we expected to get in a particular chemical reaction, let's say. So you take your 20.0 grams, subtract your measured value, your experiment, what you did in the lab, 19.8. Remember, we want the absolute value of that. Not that it matters because this is going to come out positive anyway. Divide that by 20. Because that was our accepted value. Now before I multiply by 100, I want to reduce this down. 0.2 grams divided by 20 grams. One nice thing about percent error is that it doesn't have any units, because the units cancel out. I have grams on top and grams on the bottom, which cancels out.
Dude, that's probably where he is. Just let me throw off his pudding.
All right.
We still need 4.
Now what's 0.2 divided by 20?
What ankle hurts? My wrist hurts.
0.01? Everybody agree with that?
Good to go.
Okay.
You want the answer?
Nope, because we got to multiply that by 100.
10.
So we had 1% error in our measurement.
You know what?
Dude, what if you got it over 53
Got to times it by 100 to make it a percentage. We times it by 100 and turn it into a percentage. All right, our last slide then. Oh, we got precision versus accuracy. I forgot about that one.
Well, now we're all...
We're going to skip and go right here.
I have one that's like
All right, temperature conversions. We have 2 main temperature scales that we use in science. We use Celsius a lot, but unfortunately Celsius has negative numbers. And when you calculate with negative numbers, that tends to cause a problem. So we have another scale that uses the same size amount of temperature. The Celsius amount of temperature, 1 degree of Celsius. is the same amount as 1 Kelvin is the other scale. So we've got Celsius and we've got Kelvin. Yay. So there's Celsius, there's Kelvin. The absolute coldest temperature you can get to on the Celsius scale is negative 273. On the Kelvin scale, that's where we start measuring from, is that coldest possible temperature, which is called absolute zero. It's where all molecules basically come to a stop and they don't move anymore. They might have a little bit of movement internally, but they're really not have a whole lot of energy left. They're pretty much stuck where they're at. So the Kelvin scale has no negative numbers. It starts from the coldest possible temperature and works its way up. So the boiling point of water is 373 kelvins. Of course, it's 100 Celsius. Freezing point of water is 0 for Celsius, but it's 273 for kelvins. And it's the easiest conversion there is. To get from Kelvin to get to Celsius, you take your Celsius temperature and you add 273 to it. So take a look. If I have a Celsius temperature of 0, I plug that in. 0 plus 273 gives me my Kelvin temperature, 273. If my Celsius temperature was negative 273, I plug that in. Negative 273 plus 273 is 0. Gives me my Kelvin temperature. To go the other way, if I have a Kelvin temperature and I want to get a Celsius, I just subtract 273. So that's the other equation. We'll pop that up a little bit higher.
Take your date, 78. 37.
Any questions about those conversions?
Just 7.
That's Celsius, that's Fahrenheit.
Yeah, Fahrenheit we don't like to use either because that is even more of a beast. Alright, so the next thing is a worksheet for you. Yes, go ahead.
Oh, you see you was right here.
Like, I have
All right, here's the deal. Up at the top, you're going to want to pay attention to this because I'm going to tell you what. I'm going to give you some of these problems to not do. Should be coming. Thank you for your patience. All right, so up at the top there, you have the converting of temperatures. If you see any temperature that has a degree Fahrenheit, you can cross that one out. You don't have to do that one. Mr. Gussie and Mr. Blackford wanted you guys to do that one, but I'm going to say no, you don't have to do that. Even if it's converting it to Fahrenheit or from Fahrenheit, doesn't matter which way it is. You see a degree F, you can cross that one out. Just like letter G, letter I, letter J, letter K.
Everything on that left side.
Right, not everything. Letter H. Letter H you can do on the right side.
Oh, I just didn't.
It is June 11th. I think there is one other sheet that's going to be coming up, but it's a really short one. It's really easy. One thing that you guys want to do, since we didn't go over accuracy and precision, make sure that you add that into your notes on your own at some point in time. You can go online, look up different things about accuracy and precision, but you need to know the definition for accuracy and precision. What's the difference between the two? They're not the same thing.
One's more precise than accuracy.
Accuracy is how close you are to the right answer. Precise is when you take multiple measurements. How close are they to each other? And that is all. Got about 3 minutes, yes.
Let's